Welcome to Microchip's Memory Technology Series. So, what's an FRAM? Well, FRAM or F-RAM or FERAM all stand for Ferroelectric Random Access Memory. It is random access. Just like an SRAM, you can read and write and jump around the address locations symmetrically, which means that you can read a byte of memory just as fast as you can write a byte. FRAM is non-volatile, which means the memory content is not lost when the power is turned off. And this non-volatility is FRAM's key market value. We'll learn that FRAM memory ICs are more expensive than SRAM parts, and engineers choose FRAM only if their application cannot lose current working data on any brownout or any power loss. SRAMs can't do that, so you'll pay more for FRAM, which can. Writing to an FRAM doesn't damage the memory cell. Write it as many times as you want. 100 trillion writes is a general spec number. Note that today, FRAM memory ICs come only in the lowest densities, 1 kbit up to 4 megabits. At 1 kbit, they cost about 20 cents more than an SRAM, and at 1 megabit, that difference could be as much as a couple extra dollars. Probably 95% of FRAM's volume today is serial, I2C or low-speed SPI interfaces. Now let's look at how FRAM works. In the 1950s, about 70 years ago, scientists created a crystal structure called PZT. I'll let you read the real name here. PZT has become important in volume electronics because it is piezoelectric. It's an electric dipole, which practically means, one, it creates a measurable voltage across its ends when physically stressed, like twisted or bent or squeezed. Think sensors, ceramic resonators. And two, the reverse is also true. Put a voltage across it, and the crystal will slightly deform and change some physical properties. For FRAM, the key change is that the crystal's dielectric constant can change by up to 10 times. That's a huge number that FRAM takes advantage of. Put PZT crystals as the dielectric between two metal plates, and we create a capacitor that can change in value. Voltage plus to minus like this, and the capacitor becomes small. Voltage minus to plus like this, and the capacitance changes to large. Now it takes some voltage momentum or hysteresis to cause this physical change in the PZT, which makes each dipole state stable. That is a very good thing. Back in the 1950s, that behavior looked like the iron bead memories that were popular back then. So it was named ferroelectric, and FRAM capacitors were named ferrocapacitors. Not the best name if you are a marketer for FRAMs today, since FRAM has no iron in it and magnets don't affect it. That's an MRAM problem, so FRAM suppliers have to spend time constantly correcting this misunderstanding with their customers. Okay, now let's have a logic 0 be represented by PZT position number 1 or low capacitance, and a logic 1 represented by PZT position number 2 or high capacitance. Now let's take away the voltages, and these PZT positions stay fixed. Write your 1s and 0s to the FRAM, unplug the system, put it on a shelf, come back in 10 years, and your 1s and 0s will still be there. This is what an FRAM cell looks like. This is the gate symbol with the variable PZT capacitor, and this is a cross section. Maybe this will be improved, but today the reason FRAM memories are priced higher than about every other memory type, and the reason FRAM is only available in these very small densities, is because this capacitor has to be big enough for a sense amp to measure enough charge on the capacitor plates to tell the difference between a 1 and a 0 accurately. Also, reading the FRAM bit is destructive. That sounds bad, but it just means to read the bit, voltage is pushed against one plate of the capacitor to force charge on the other plate over to the sense amp. Lots of electrons, because of high capacitance, means it will be called a 1. Not so many electrons means it will be called a 0. Since voltage was used to read this bit, the PCT position may have accidentally been changed, so the 1 or 0 value has to be written back onto the capacitor to restore that value at the end of the read function. There's no risk of losing information through this process. However, that extra time to rewrite the bit makes FRAM slower than other memory types, and that is why FRAM is sold primarily as an I2C or low-speed SPI serial memory, where the memory read and write speeds are just not that important. Since the 1 and 0 values are stored inside the dielectric, and the electrons that are being used in the process are just moving on and off the plates for both reading and writing these cells, there is no physical damage to the material during writes, and so 100 trillion writes are possible. And since no current flows through the memory cell on either a read or a write function, FRAM happens to be a very low power RAM solution. And again, FRAM is not ferro, not iron, so it's not bothered by big magnets or electric motors. That is an MRAM problem. See our other videos to learn more details about various memory technologies, terms, and other memory concepts.